Hello students, in today's lecture we will start gravitation and go through the topic 7.1, 7.2 with an example 7.1 from NCERT. This is disclaimer. Strategy for competitive exams. We will start by mastering Kepler's law. We will develop a strong understanding of Newton's law of universal gravitation. Practice numerical problems involving gravitational field and potential. Clear understanding of orbital mechanism and satellite motion. Focus on the concepts of escape velocity and gravitational potential energy. Understand variations in G at different heights and depths. Solve problems from past year JEE and NEET papers. Recommended books. Please visit our website forum.prota.ai to get suggestions of books and guidance. Learning objectives. By the end of this session, you will have a solid understanding of Kepler's law and their mathematical derivation. In today's lecture, we will cover 7.1 Introduction, 7.2 Kepler's laws, then we will solve an example 7.1. Alright. So understanding history of gravitation. Let's begin with Galileo. Galileo demonstrated that all objects, regardless of their mass, fall towards Earth with the same constant acceleration. This was a groundbreaking discovery at the time. Alright. A feather and hammer would fall at the same speed in vacuum. The Earth's gravity pulls everything towards its center with the same acceleration, which is why this fall when you drop them. Alright. Ptolemy proposed the geocentric model, placing Earth at the center of the universe with all celestial bodies. Copernicus and Aryabhatta suggested that the Sun was actually the center, heliocentric model, with planets including Earth orbiting around it. This heliocentric model was later proven correct. Alright. Starting with the historical observations made by Tycho Brahe. So let's begin with Tycho Brahe, who lived from 1546 to 1601. He dedicated his life to meticulously recording the positions of planets using only his naked eye. Brahe data didn't just sit idle. It was analyzed by his assistant Johannes Kepler, who lived from 1571 to 1614. Kepler's role was important as he transformed Brahe's extensive data into meaningful insights. From this data, Kepler was able to derive three elegant laws of planetary motion, known as Kepler's laws. These laws were instrumental for Isaac Newton in formulating his universal law of gravitation. Understanding the Kepler's laws. There are three laws given by Kepler. First, law of orbits. Second, law of areas. Third, law of periods. So let's explore Kepler's first law, also known as law of orbits. Kepler's first law states that all planets move in elliptical orbits with the Sun at one of the foci. So, Sun having at one of the foci. This means that the path of a planet around the Sun is not a perfect circle, but an elongated circle or ellipse. In figure, you can see the ellipse traced by the planet with the closest point to the Sun, called the perihelion, and the furthest point called aphelion. Aphelion or perihelion. This one is perihelion, and this one is aphelion. Notice how the Sun is not at the center but at one of the focal points of the ellipse. Understanding properties of ellipse. An ellipse is a closed curve that can be drawn by fixing 2 points known as the foci, labeled as f1 and f2. f1 and f2. For any point on the ellipse, the sum of the distances from the two foci is constant. This is a defining property of ellipse and is expressed mathematically as tf1 plus tf2 is equal to 2a. Here a represents the semi-major axis. So semi-major axis OA is equal to OP is equal to A. Now P represents the perihelion, which is a point where the orbiting body, example a planet, is closest to the central body. So focus on perihelion, this one, marked as P on the figure. This is the point where the orbiting body such as planet is closest to the central body like the Sun. A represents the aphelion. At this point, orbiting body is furthest from the central body. This is a point where the orbiting body is furthest from the central body. Let's discuss the eccentricity of an ellipse, which is a measure of how much the ellipse deviates from being a perfect circle. The formula for eccentricity is given by E equal to C by A. This is the formula. So here we will understand the types of motion. So let's start by classifying motions based on the energy of the particle. So first type of motion is bounded motion. Second type is unbounded motion. So understanding the bounded motion. So in bounded motion, a particle's total energy is negative. It means for a particle's total energy negative, uh, the bounded motion, the negative energy indicates that the particle is trapped in a gravitational well, unable to escape. So such motion exhibits two, R minimum and R maximum, for more or more extreme points where the total energy matches the potential energy, leading to zero kinetic energy. This occurs at two or more points, so R minimum and R maximum. R minimum and R maximum. Bounded motion is characterized by eccentricity between 0 and 1. Alright? Specific examples of bounded motion: circular orbits where the eccentricity is 0, elliptical orbits where the eccentricity is less than or equal to 1. So E equal to 0 and E less than equal to 1. Alright? Understanding the unbounded motion. In this scenario, the total energy of a particle is positive, meaning E is greater than equal to 0. This is crucial because it indicates that the particle has enough energy to escape the gravitational pull. So we have the concept of a single extreme point denoted as R minimum. R minimum. At this point, the total energy equals to the potential energy, which means the kinetic energy drops to 0. So this occurs when eccentricity E is greater than equal to 1. So parabolic orbits equal to 1 and hyperbolic paths E is greater than 1 represents unbounded motion. Alright? We are going to explore Kepler's second law, also known as the law of areas. Kepler's second law states that the line joining planet to the sun sweeps out equal areas in equal intervals of time. This means that a planet moves faster when it is closer to the sun and slower when it is further away. So let's look at the diagram, or we can say figure, to visualize this concept. So planet P moves around the sun in an elliptical path, and the shaded area is the delta A, swept out in a small interval time delta T. This law is a direct consequence of the conservation of angular momentum. Angular momentum is a measure of the momentum of a body in a rotational motion, and it remains constant if no external torques acts on the system. When the planet is further from the sun, it moves slower. This is because the gravitational pull is weaker at greater distances, allowing the planet to cover less distance in the same amount of time. Conversely, when the planet is closer to the sun, it moves faster. The stronger gravitational pull at closer distances cause the planet to accelerate, sweeping out the same area in a shorter time. Understanding planetary motion in regard to law of areas. So notice how planets in elliptical orbits experience changes in elliptical energy. This is because their speed varies depending on their position in the orbit. The figure here illustrates an elliptical orbit, which is a key to understanding these variations. Remember, The shape of orbit affect how fast or slow a planet moves. So now let's focus on what happens when a planet is near the perihelion, the point closest to the sun. So at this position, perihelion, the planet's kinetic energy is at its highest, causing it to move faster. This increase in speed is due to the gravitational pull being stronger when the planet is closer to the sun. While when a planet is near the aphelion, the point furthest from the sun, its kinetic energy decreases and it moves slower. This is because the gravitational pull is weaker at this distance. We are going to explore the fascinating topic of planetary motion, specifically focusing on the law of areas. So, as you can see in the figure, the orbit is elliptical. This means that the distance varies as the planet moves. So here we have a mathematical expressions for these distances. At the perihelion, here the distance is given by r minimum is equal to 1 minus e. R minimum is equal to a into 1 minus e. And at aphelion, its r max is equal to a into 1 plus e. In these equations, a represents the semi-major axis of the ellipse and e. So we see that the sum of the perihelion and the aphelion distances equals to twice the semi-major axis, expressed as r minimum plus r max. So 2a is the semi-major axis. Alright. So here we will understanding the mathematical form of Kepler's second law. For a central force, the angular momentum denoted as L is conserved. This means that the angular momentum remains constant over time. A central force is one that is directed towards or away from specific point as the center of force. So consider the area swept by a planet in a small time interval delta t. Alright, denoted as delta A. This visual representation shows a planet moving around the sun in an elliptical orbit. So the mathematical expression for the area swept out is given by delta A is equal to 1 by 2 into a mode of r cross v into delta t. Here r is the position vector of the planet and v is its velocity vector. Alright, so the formula for delta A is very important for the exam. So continuing the mathematical derivation of laws of areas. So rate of area swept dA upon dt is dA upon dt is equal to 1 by 2 r cross mode of r cross v, where r is the position vector and v is the velocity vector. Next we consider the magnitude of angular momentum, represented as mode of L is equal to mode of r cross mv. Here m is the mass of the planet. Angular momentum is a measure of the rotational motion of the planet around the sun. So simplifying the expression for angular momentum, we have mode of L is equal to m into mode of r cross v. This step highlights the relationship between angular momentum and the cross product of the position and velocity vector. So we can express the magnitude of the cross product as mode of r cross v is equal to mode of L divided by m. Alright. Now we have dA upon dt is equal to 1 by 2 mode of r cross v. Here r is the position vector and v is the velocity vector. So we substitute the expression for magnitude of the cross product. So r cross v with mode of L by m. Here L represents the angular momentum and m is the mass of the object. So equation is dA upon dt is equal to 1 by 2 into mode of L by m. Since the angular momentum L is conserved in the case of central forces and the mass m is constant, it follows that the rate of area swept out dA upon dt remains constant. Therefore, we conclude that dA upon dt is constant. This principle is known as Kepler's second law of planetary motion. Alright. We are going to explore Kepler's third law, also known as the law of periods. So this law states that the square of the time period of revolution of a planet is directly proportional to cube of semi-major axis of its orbit. So mathematically we can express Kepler's third law as t square is directly proportional to a cube. Here t represents the orbital period, which is the time taken for one complete orbit. And a is the semi-major axis, which is essentially for the average distance from the planet to the sun. So where t is the orbital period, a is the semi-major axis. Understanding verification of Kepler's law from observed data. Here we have a table 7.1 which represents the data from measurements of planetary motions. So we have a table listing planets, their semi-major axis A in units of 10 raised to the power 10 meters, their orbital speed t, and in years, and the calculated value q is equal to t square by a cube in 10 raised to the power minus 34 y square per meter cube. So for first Mercury, the value of A is 5.79 and T 0.24. Similarly, Q 2.95. For Venus 10.8, T 0.615 and Q 3.0. Earth is 15 and T is 1 and Q 2.96. For Mars, A is 22.8 and T 1.88 and Q 2.98. Similarly for Jupiter, Saturn, Uranus and Neptune. Alright, the A, T and Q values. So in the given table 7.1, quotient Q is calculated as T square upon A cube in units of T raised to the power minus 34 y square per meter cube. So for all 8 planets, the Q value of Q is approximately constant, ranging from 2.95 to 3.01. This constant value confirms Kepler's third law of planetary motion. It's a powerful validation of the law, showing that the ratio of the square of the orbital period to the cube of semi-major axis is indeed constant for all planets. So since third law of Kepler's says that T square by A cube is equal to constant. Alright. Now example 7.1. So let the speed of the planet at the perihelion P in the figure 7.1 VBP and the sun planet distance SP be RP. Relate RP VP to the corresponding quantities at the aphelion. Will the planet take equals time to traverse BAC, BAC, BAC and CPB. Alright, let's see the solution. So the given terms here, or we can say first, let mass of the planet is mp, denote angular momentum at perihelion is lp is equal to mp rp vp, and angular momentum at aphelion is la is equal to mp ra va. All right, so from the angular momentum conservation, we express the conservation of angular momentum mathematically. lp is equal to la. So the equation is mp rp vp is equal to mp ra va. So mp cancel out, the remain. Similarly, we can say to equate vp upon va is equal to ra upon rp. This tells us the ratio of the velocities at the perihelion and the aphelion is inversely proportional to the ratio of their respective distances from the sun. The formula Vp upon Va is equal to Ra upon Rp shows that the ratio of the speeds is inversely proportional to the ratio of the distances. Since the distance at the aphelion Ra is greater than the distance at the perihelion Rp, it follows that the speed at the perihelion Vp must be greater than the speed at the aphelion Va. This means the planet moves faster when it is closer to the sun, and area SBAC is larger than SBPC. So from Kepler's second law, equal areas are swept in equal times. Hence the planet will take longer to traverse BAC and then CPB. Derive Kepler's third law from Newton's law of gravitation for circular orbits. This is very important concept. So we will see how Kepler's third law can be derived from Newton's law of gravitation. So in a circular orbit, the centripetal force required to keep an object moving in a circle is provided by gravitational force. So here the equation that represents this balance of forces, the centripetal force given by mv square by r is equal to gravitational force gmm divided by r square. This gives orbital speed. So v is equal to under root gm by r. All right. So periods of circular orbit, t is equal to 2 pi r divided by v. Substituting the expression of velocity in our period formula. So t is equal to 2 pi r into under root r by gm. All right. Now, simplifying. Here we have the expression for the orbital period t is equal to 2 pi under root r cube by gm. So squaring both sides, you will get t square is equal to 4 pi square upon gm into r cube. This is another form of Kepler's third law. As Kepler's third law, t square is directly proportional to a cube, or t square is equal to k r cube. So here k is equal to 4 pi square upon gm. K is a constant. Now these are the main points to be remembered from today's session. So this chapter begins with early observations of gravity and historical development from Ptolemy to Copernicus. Tycho Brahe observations were crucial for Kepler's to formulate his three laws. Kepler's first law, planets move in elliptical orbits with the sun at one focus. Kepler's second law, equals area are swept in equals times, laws of areas. Kepler's third law, t square is directly proportional to a cube, relationship between orbital period and semi-major axis. This law helped Newton develop his universal law of gravitation. So this law applied to any object orbiting under central force. Now we have some practice questions. First, what shape are planetary orbits according to Kepler's first law? Who made detailed planetary observations that helped Kepler formulate his laws? What is the point of a planet's orbit closest to the sun is called sun? When a planet is closer to the sun, does it move faster or slower? According to Kepler's third law, if planet A has twice the orbital radius of planet B, how many times longer is planet A's period? Alright, so this is homework for these questions are homework for you. Thank you for your attention.